Imagine making an omelette with a recipe that says mix some cornstarch with a lots of egg and a little milk and some butter and bake for a while. What do you think? How helpful is this? Your recipe might not be same with mine, right? Now let's consider this one. Mix 5 eggs with 30 ml of milk, add 20-gram butter and bake for 3 minutes. Now with this recipe, anyone, anywhere in the world can make the exact same omelette. This is the power of precision, and precision matters in science. And this precision comes from physical quantities and their units. And in our today's lecture, we are going to discuss what are physical quantities, why these quantities are so important, their types, and then we also analyze their units. As we already discussed, that science cannot survive with the terms like some and little of something. For our experiments to be correct, we need clear measurements with numbers and units. So, for our experiments to be correct, the measurements should be precise. And this precision matters a lot. Why? As in 1999, NASA lost $125 million due to a mistake in units. Mars climate orbital were lost because one team used empirical units while other team used metric units. Due to this tiny difference, the spacecraft enters it too low into Mars atmosphere, and as a result it disintegrates. This shows us that in science and engineering, using correct physical quantities and units is very important. It's not an optional thing. It's life or death for a mission. So now let's see what are physical quantities. Measurable properties of a phenomena, body, or substance are called physical quantities. And physical quantities consist of two different parts. One is the number of physical quantity, and other thing is the unit associated with that number. Like 5 meters. So here 5 is the number and meter is the unit of length. 10 seconds. 10 is the number and second is the unit of time. And similarly 2 kilogram, for 2 is the number and kilogram is the unit of mass. So if you use numbers without units, they are meaningless. Like if I say 20, there is no meaning. But if I put Celsius here, so now it means 20 Celsius of temperature. So it makes sense now. Now the question is, are all physical quantities are of the same type? There are two different types of physical quantities. One is base and other is derived quantity. So base quantity, as from its name it is clear, they are basic, fundamental, and they don't depend on any other quantity. They are independent. While derived quantities, they are not fundamental and they depend upon base quantities. The base quantities are length, mass, time, temperature. And if you see derived quantities, the examples are speed. And speed, as we know, is equals to length by time. So length and time, these two are base quantities, but when they combine, they form speed. So that's why speed is derived quantity. Similarly, force is made up of many base quantities, and so on. Now let's analyze the base quantities with their units. As there are 7 base quantities and their names are here: length, mass, time, temperature, electric current, luminous intensity, and amount of substance. So here the length is represented with symbol L, a mass with m, time with small t, and temperature with capital T, and similarly electric current with I, and so on. If you see their SI units, the SI unit of length is meter, and it is represented with unit. Its unit is represented with symbol m. The SI unit of mass is kilogram, and that is represented with kg. And similarly for time is second. For temperature, it's Kelvin, represented with K. And for current, it is ampere, represented with A. For luminous intensity, the unit is candela, and it is represented with CD. And for amount of substance, the unit is mole, and it is represented with MOL. So from all these units, we will mostly deal with these three in this course: mass, kilogram, and second. Also, when we deal with temperatures, we will use Kelvin as well. Now let's analyze derived quantities and their units in detail. These are like recipes of physics. Like in recipe, you need ingredients to make the recipe. Similarly, to make the derived quantities, you need your ingredients are the base quantities. Like here, speed is equals to length over time. So these two are base quantities. When these two combine, that forms speed, and hence this is a derived quantity. And if you see its unit, it's meter per second. So unit is also called derived unit. Acceleration is speed over time. So it also consists of three different base quantities. So hence we can call acceleration as a derived quantity. Force is mass time acceleration. So kilogram meter per second square. So you see here there are 4 different base quantities. So these base quantities combine to form the force. So we can call force as derived quantity. Pressure is also derived because it is made from force and area. And similarly, energy is force times distance. As work is equals to force times distance, so work is a form of energy. So you can say that this is also a derived quantity. Now let's check our understanding. So far, speed is a base quantity. Is it true? False, because speed is made from length and time, so it is a derived quantity. Hence, it is a false. Kilogram is the SI unit of mass. Right, is true. Force is derived from mass and acceleration. True. Temperature is measured in candela. It's false. Now let's do another activity of matching these columns. Here you see pressure, energy, length, electric current. On the other side, ampere, meter, pascal, and joule. So what is the best option for pressure? So pressure is related with, what is the unit of pressure? Pascal. So Pascal is the unit of pressure. Energy is measured in joule. Length is measured in meter. And electric current is related with ampere. Now student, let's analyze this example 1.2. The period of simple pendulum is defined as the time taken to complete one full cycle. It is given by the following equation. The t is equals to 2 pi L by G with the root, where here L is the length and G is the gravitational field strength. So now the question is to find the derived SI unit of G, the gravitational acceleration. So now let's start. As we know the given formula, in given we have a formula and we require the unit of G, gravitational acceleration, the SI unit, and we can start with the same formula, but now we need to take the square on both sides, and as we take the square on both sides, we will get t square equals 4 pi square L by G. By rearranging this equation, we can get G equals 4 pi L by T square. 4 pi square L by T square. And now let's analyze the units of all these terms one by one. 4 is a number and pi square is also a number, so it is unitless. But L is length, so its unit is meter, and T is time, its unit is second. So if we take T square, it makes second square. So if we place all these here, we will get G equals m over second square, and that is what the SI unit of gravitational acceleration. What did we learn today? We start from a recipe of omelet, and then we discuss about the disaster made by NASA scientists, and through that we understand that the SI system of unit is really important. We also analyze that physical quantities give us precision through these examples, and precision is necessary for science. We describe the physical quantities and they consist of number plus units, and there are two different types, base and derived quantities, and they have their units. So there are 7 base quantities and 7 base units. Similarly, there are many derived quantities and many derived units. So this is all from our today's lecture. So this is our homework, page 20, question 1, 2, 3, and 4. Thank you very much.